Welcome to this short series on how plants convert light into biomass. The radiation interception efficiency is the fraction of PAR that is intercepted by the vegetation and that may be potentially used for the photosynthesis to produce biomass. This quantity is called FEPAR, the fraction of intercepted PAR. It is also called FEPAR, the fraction of photosynthetically active radiation absorbed by the vegetation. In fact, almost all the light intercepted by the leaves is absorbed by the chlorophyll pigments in the visible domain, which makes both quantities very close together. FEPAR is a very good proxy of FEPAR. FEPAR is also called sometimes light interception efficiency or radiation interception efficiency. The fraction of intercepted PAR, FEPAR, varies between 0% to 100%. It equals 0% for bare soils, or when the vegetation is fully senescent, with no more chlorophyll pigments that can transform light into biomass. FEPAR equals 100% for very dense green vegetation. The fraction of intercepted PAR depends mainly on two main factors: the vegetation development and architecture, and the illumination conditions, including the position of the sun and the fraction of diffuse radiation. Vegetation development may be measured by the green area index, the area of green elements per unit horizontal ground area. The green elements correspond to leaves, stems, or reproductive organs. GEI is expressed in a square meter of green vegetation area per square meter of ground area. The more green elements, the higher will be the radiation interception efficiency. There is generally an exponential relationship between the green area index and FEPAR. FEPAR equals 0% when green area index equals 0. FEPAR reaches 100% for GEI values larger than 3 to 6. The rate of increase of FEPAR with GEI is controlled by the vegetation architecture. When the leaves are almost horizontal, which is called a planophile vegetation, FEPAR varies strongly with GI and reaches 100% for GI around 3 square meter per square meter. Conversely, when the elements are mainly vertical, which is called an erectophile vegetation, FEPAR varies more gently with GI and reaches 100% for GI larger than 6 square meter per square meter. In addition, the orientation of the elements, in addition to the orientation of the elements, their spatial distribution is also important. When the elements are clumped together, such as for row crops, the interception efficiency is lower as compared to the situation where elements try to avoid themselves to intercept light more efficiently. Each species develops a particular architecture in order to provide an optimal trade-off between high light interception efficiency favorable to photosynthesis and a lower one that will minimize the transpiration. Farmers and breeders may also play on vegetation architecture through sowing patterns, pruning techniques, and selection of particular plant structure. The second factor that impacts the radiation interception efficiency corresponds to the illumination conditions. The interception efficiency of the diffuse incoming radiation component is generally larger than that of the direct incoming sun component. Further, low sun positions will increase the radiation interception efficiency by increasing the optical path length in the vegetation. In the next episode, I will describe how to measure the interception efficiency.